The last topic of Calculus BC deals with vectors, and today we're going to look at what a vector is and do some work with them. A vector is a mathematical measurement of magnitude and direction. We're going to represent vectors usually with these pointy brackets, A comma B. You can think of them as an ordered pair. You can see a picture A comma B over here, but a vector is much more than just an ordered pair. It's actually representing, envision an arrow here. The length of the arrow is what we call the magnitude. The direction, even writing this in components the way we have with an x coordinate and a y coordinate, you can see just doing so indicates a direction coming from the origin. Reading this paragraph, a two-dimensional vector, of course, then has components A and B, standard representation of arrow A comma B. It's the arrow from the origin. The magnitude, also represented by absolute value, is simply the length of that arrow. The magnitude, of course, is going to be found via the Pythagorean theorem. And we can see, just as up here, if we had a x-coordinate of A, a y-coordinate of B, that length would follow from the Pythagorean theorem. So if we're ever asked to find the magnitude, we're finding the length of that arrow, the Pythagorean theorem would do the trick. Direction angle. A direction angle is the smallest non-negative angle theta formed from the positive x-axis as the initial ray, and V, the arrow itself, is the terminal ray. Most of the time we will write this in radians, but a lot of application problems with navigation might use degrees as well. We'll see that a little bit. Head minus tail rule. Well, let's just say that you have a vector QR, meaning that you begin at point Q, you go in R's direction. You have -4, 2 for the coordinates of Q, -1, 6 for the coordinates of R. If you'd like to have another way to represent the vector emanating from the origin, we can use the head minus tail rule. The head minus tail rule works out this way. It says, look, take your coordinates and simply subtract them. Take x2 minus x1, y2 minus y1. So if I'd like to use head minus tail for this vector here, I would say 6 minus -4, and then, oh, I'm so sorry, made a mistake there. For my x, it would be -1 minus -4. That's your x2 minus x1. And then you'd have y2, which would be your 6, minus y1, which is 2. -1 minus -4, of course, would be a 3. 6 minus 2 would be 4. So the head minus tail rule would say that vector QR would be equivalent to the vector 3, 4. These vectors are parallel, but they will be going in the same direction, and of course they'll have the same magnitude. And we're going to prefer to have our vectors starting from the origin. Real quickly, let's take a look at example 1. Find the magnitude and the direction angle of the vector -1, √3. Well, -1, √3, we're going to go -1 steps to the left. We're going to go up √3. And I can't stress enough, what a vector is, it's representing an arrow. So really we're asked to find the length of that arrow. We could call this R if you'd like. We can certainly use the Pythagorean theorem. Even if we use -1 in there for a length, squaring that will disappear. 3 plus 1, of course, is going to be 4, and R would equal 2. So the magnitude of this vector is 2. Again, the Pythagorean theorem is what we can go to time and time again. By the way, in this instance, you might have noticed this is also a very famous 30, 60, 90 right triangle. That would very quickly allow you to know the magnitude immediately. It can also help you know that this is an angle of 60 degrees across from a root 3. We could also find this angle in terms of degrees or radians via trig. Tangent of theta would be the opposite over the adjacent. Ignoring negative signs for a minute, you could see that theta would be inverse tangent of root 3, and that would mean theta would be pi over 3, or 60 degrees. But the direction angle is not pi over 3. The direction angle, if you said it was pi over 3, you'd be in the first quadrant. So making an adjustment, you know that this is pi, and we had a reference angle of pi over 3, we'd be at 2 pi over 3. Similarly, as we look at number 2, find the component form of a vector with a magnitude of 3 and a direction angle of 40 degrees. So we could say, well, look, we have a direction angle of 40 degrees, we have a magnitude of 3. Could we find our x and y components? Well, going back to SOHCAHTOA, SOHCAHTOA can be very, very helpful. We can say the cosine of an angle is the adjacent all over the hypotenuse. Similarly, sine is opposite over hypotenuse. And certainly we may solve for a decimal approximation, but honestly that's not even necessary. I have my exact coordinates right here, and I'm going to write my components simply as 3 cosine of 40 degrees, comma 3 sine of 40 degrees. Okay, so that can certainly be done. Let's take a look real quickly at some neat uses of vectors. You can add 2 vectors together. Getting vectors into components is delightful because adding a vector u and v just means adding their x components together, adding their y components, and writing them in component form. In other words, add these x components, u1 plus v1, that's your new x component. Add u2 plus v2, that's your new y component. Multiplying a scalar is just a number. It does not have a vector tied to it. It doesn't have any direction to it. So just some coefficient out in front of a vector, multiplying, and you'll multiply that number to both components. The opposite of a vector just means multiply by -1. So real quickly, let's take a look at a few problems. U plus v. Well, add the x components together, -1 plus 4. Add the y components together. My goodness, we will just have 3, comma 10. We are done. 2u, if you multiplied 2 to both components for u, you'd have -2, comma 6. 3 times v, well, 3 times 4 is 12. 3 times 7 is 21. Subtracting, you're effectively just subtracting the x components as well. Take your y component of 6 minus 21. We could simplify that. We'll have -14, comma, -15. Again, our answer is a vector. What about 1/2 u? Well, 1/2 u means take half of u's components. Half of the x component would be -1/2. Taking half of 3, you get 3 over 2. But what does this absolute value mean? It really means find the magnitude. And the magnitude, as we said earlier, is very simply the Pythagorean theorem. We could graph this out with an x component and a y component, but in the end, we're going back to the Pythagorean theorem. -1/2 squared is 1/4. 3/2 squared would get you 9/4. Add these together, you'll have 10/4. Now, of course, that would become the square root of 10 all over the square root of 4. And we all know the square root of 4 is just a2. Okay, well, taking a look at many properties of vectors, thankfully so much of this is going to hold true with what we have seen with real numbers. The commutative property, u plus v is equal to v plus u. Adding vectors together, order doesn't matter. The associative property applies to the addition of vectors. If you're adding three vectors together, it doesn't matter which two vectors you add together first. Just continuing on, you can see quite a bit of the same properties. I'm going to have to stop here. We're having a little bit of an interruption. We'll pick up again very, very soon.